Hey everyone! Today we're going to be talking about integrating trig functions. Now, when we did differentiating trig functions, I put on the board a diagram that sort of helped to remember the pattern that we were dealing with. I'm going to use that same diagram today, but in reverse, which is pretty much what integration is. So if you haven't had an opportunity to, please put that diagram at the top of your page. I'm also going to write it right now. So you'll notice that this is the diagram that you should have on your page. I basically am going to spend time today going the opposite. So notice here I've put that in blue arrow in the opposite direction. So please have this at the top of your page. I find it super helpful, and we're going to be referring to it throughout the lesson. So using my diagram, I know that the derivative of the sine function is cos x, and I know that the derivative of the cos function is minus sine x. And remember, tan, as always, is the odd guy out. He has to have his own special thing, so the derivative of the tan function is secant squared x. So using that information, I'm going to go backwards now and understand that the antiderivative of the cos function gives us sine x, remember the plus c, and then the antiderivative of the sine function is equal to minus cos x plus c, and that the antiderivative of the secant squared function is the tan function plus c. So we're going to try some examples. I encourage you to pause the video right now, try the examples yourself, then unpause the video to check your answers. I think this is a really good way to go about doing it. So the first example says the integral of 2 sine x minus cos x, and the second one says 3 over cos squared x minus 2 over x plus root x. I encourage you, if you need to, especially for the second one, change the form before you take the integral. Give it a try. So you'll notice that the first one is pretty simple. It's minus 2 cos x minus sine x plus c. However, the second example, it's really important to change the 3 over cos squared x to 3 secant squared x so that you can notice right away that the integral of that is tan x. So my integral is 3 tan x minus 2 ln x. So hopefully you took a moment to notice that if I raise that to 2x to the negative 1 and I tried to take the integral of that, I would get x to the 0. It wouldn't work, so that's my hint that, again, it's a ln function. And the last part, x to the half, is 2/3 x to the 3 over 2. Sorry, cut that little error there. And then don't forget the plus c. Okay, well, the next part now says let's add another element, meaning let's add a constant inside the bracket. In that way, when I take the antiderivative, or the integral, I need to remember to divide by the derivative of the inside bracket. When I take the integral, here you'll notice that the integral of cos a to the x is 1 over a sine ax. So please remember that the bracket doesn't change, it stays the same for each of them. So the rule is the same. All I've now added is this new element here where I'm dividing by the derivative of the inside bracket. Give the next two examples a try. For the first example, if you're having any difficulty, perhaps changing the form so that the constant in front of the x is obvious that you've left it out front. That might actually help you take the derivative. And by derivative, I actually meant antiderivative. So you'll notice here, 1 divided by a quarter is 4, so that's how we get the constant out front here. Try the next one. And so here you'll notice that pi over 2 is the constant here, so when you take 1 and divide by pi over 2, you get 2 over pi in front. And that again here, when you take the antiderivative of this, you get another ln function over here. Make sure that you put your ln function in absolute value bars. Okay. And now we add the last element being a constant added to the function. Well, this doesn't change the antiderivative that we just did. All it changes is the bracket, because now the bracket is different. Now don't get a little intimidated by all the letters that are there, the A's, the B's, and the C's, Basically, we're following the exact same rule that we just did. If you have an opportunity, try the next two examples and then check your work. The first example is pretty straightforward. Nothing too complicated about it. The second one, however, involves not only an exponential function, so you have to remember how to take the antiderivative of an exponential function, but it also involves 4 over cos squared 2x. The other way that you can write that is 4 secant squared 2x, and that might actually help you realize that the antiderivative is tan x. Finally, our last example. This one here is a great example of an IB style question. It gives you the derivative, it asks you to find the original function, and it gives you a last little piece of information. That information there is to help you find c. Give it a try. Setting up the first line should look like this. Now take the antiderivative. When you take the antiderivative, you get this. Next, plug in that last piece of information right there to find c. This is where your true test of trig functions comes in. Cos at 0. Use your cos curve to identify that cos at 0 is equal to 1. When you do so, you get 4 is equal to minus 2 plus c, so that makes c equal to 6. Your final answer is f of x is equal to minus 2 cos x minus 2/3 the square root of x cubed plus 6. Have a good try at the homework. If you have any questions, please come in and see me.